All right, clip number 2 on section 2 of finding arc measurement. This is where we're going to apply some of that theory we just talked about in the last clip and apply it to some specific examples. Computation, calculation, algebra in this section is actually very, very basic. Okay, it's barely going to be calculating at all, only if there's some sort of variable involved, and even then it's not going to be terribly difficult. It's really just going to be about identifying what's the central angle, okay, what's the size of that slice, so to speak, and then using that to find the other pieces. For instance, our first example today here in the margin on the left-hand side, you will start with a diagram. Surprise, surprise, it's a circle. And they're basically going to be cutting it up into some slices. Here is again where we're going to be using that initial fact about circles, the fact that all circles have 360 degrees in them. I can use that fact to find every single slice that's missing, essentially, assuming I've been given enough information. All right, so in this diagram, I'm asked to find each measurement. There'll be an A, B, and C. I'll get to those in a second. Initially, we're told the following. We are given the diagram, and we're told that segment RT, R to T, is the diameter of this circle. That matters. That means it goes through the center. It's essentially cutting the circle in half. So fundamentally, even though they didn't tell me explicitly what the degree measurement was, that means that this semicircle on the upper part has to be 180 degrees. That also means this lower half must also be 180 degrees. That diameter is going to chop that circle directly in half. So that's an important fact right there. All right. Another way that they could have said it is they might not have said RT as a diameter. They might have just said, hey, this is circle P. Why would that have mattered? You will always see the name of a circle named after the center of that circle. And so if they called it circle P, that would force point P right here to be the center. And since that chord is going through the center, that would have to be a diameter. So that's just another way they might have said it, all right, just to prepare you for that. Okay, so in the diagram, they also tell us that this slice is 70 degrees. For the record, that also means that this arc ST right here is also 70 degrees. It's based on the central angle. Simple enough for that one. All right, but here's what I could use to find out the missing slices. Again, because RT is a diameter, first off, that forces this slice, this half of the pizza, to be 180 degrees. So I actually know the degree measurement of that slice. Okay, so I could use the fact that that's 180, that's 70. I could add those together and find what's left over for the 360 to fill in this guy. Or I can think in terms of, hey, this is half of the pizza as well. So that must be 180 degrees. So if that guy's 70, what's left over to get to 180? And I figure out that that guy's 110 degrees. Okay. The important part about that little puzzle, filling in those slices as far as the degrees, is that will directly translate to what the arc measurement is going to be. And that's going to lead me to A, B, and C here. All right, so one other thing to point out here. Here's where, again, we're going to see that geometric notation. You'll notice that each of these guys has that little arc above it. That means I'm dealing with arc measurement. I get asked this a lot. They're like, what does this M stand for in front? You've seen the same thing for angle measurement. They throw the little M in front when we're actually talking about the M stands for measurement, because fundamentally there is a small difference, a subtle difference, but a small difference between a geometric object of an angle or an arc. It's just an object. When I throw in that M, now I'm actually talking about how it actually measures, the quantifiable measurement of it. So the measurement of an angle would be in degrees. The measurement of an arc is also in degrees. All right, the other piece of the notation here, here's where we see minor arcs versus major arcs. 2 letters, RS, is going to be the shortest distance between the two. So R to S is literally this arc right here, that slice. Whereas RTS, the 3 letters, means it's a major arc, which means I'm going the long way, right? So go from R to T to S. It's referring to this whole Pac-Man shaped type of thing on this side. Right? So, and then the last one, RST, is going to go from R to S to T. So there's another major arc right there, even though technically that one's going to turn into a semicircle. All right, so now to the answers. Again, I'm just going to talk through these really briefly because what you would probably want to do, the fastest way to deal with these ones, particularly when you have like an A, B, C, D, E, F, multiple pieces, At the very beginning, just see if you can start filling in the rest of the slices for the degrees. Okay, this guy was 70. That's what we were given. I know this RT was a diameter, forcing this slice on this side to be 180 degrees. And that leaves 110 degrees left over for RS, whether you did it by adding everything up to 360 or figuring out that this was a semicircle as well and subtracting 70 from 180. Either way, we find out that this slice here is 110 degrees. Let's use that information to solve these guys. All right, part A, measurement of minor arc RS. R to S is this slice right here. In order to figure out that arc measurement in degrees, I need the central angle. As I just talked about, that's 110 degrees. What's the measurement of arc RS? 110 degrees. Done. No real algebra involved there. Part B, major arc RTS. Again, I want it in degrees. R to T to S. So essentially, I'm adding up this slice and this semicircle slice. That's the arc addition postulate right there. The first theorem that we talked about in the last clip. Arc addition postulate says this. All right, I'm trying to find this major arc measurement. If I don't explicitly know what that entire arc is, I can add up the pieces that make up that arc. In this case, there's only two. The 70 degrees here and the 180 degree slice or half of the circle on this side. So the 180 degrees plus 70 degrees, measurement of major arc RTS is 250 degrees. Done. That's basically just arithmetic. All right, part C, major arc RST, R to S to T. The giveaway here is that since R and T are the endpoints, this is literally the diameter, so it's just chopping the circle in half. I could either think of it in terms of, because it's a diameter, part C, RST has to be 180 degrees, or since I figured out, again, using the arc addition postulate, that this was 110 and this is 70, I could add both of them together and I still get to the 180. Part C, arc RST is 180 degrees. Done. Okay. As far as like work expected and that sort of thing, the most work you'd really have to show is like how you achieve the degrees in each slice. After that, you're just identifying which arc is which. Okay, on to the next example. Staying here in the margin, you'll see these solutions worked out with explanations and stuff in the Google Classroom as well if you need to see more. All right, in this question, this is going to be dealing with the arc congruence stuff. Okay, and our job here in this series of questions in the margin is to tell whether the given red arcs, hopefully you can see which ones are the red arcs, I'll point them out when we get to them, whether the given red arcs are congruent to one another for A, B, and C. So here, next to this problem, whether you're putting it somewhere else, some other explanation, again, this is essentially going to break down to a two-step check. Step number one, are the circles congruent to each other? What we're going to find for part A here is it's just one circle. So yeah, it's congruent to itself. Okay, but for B and C, I'm going to be dealing with multiple circles. So I need to check, are the circles congruent to each other? If they are, then yes, it is possible that the arcs can be congruent, but I need to check step two. If the circles are not congruent, they're simply not going to be congruent, the arcs. Okay, so we'll see that with B and C. All right, so step number one, are the circles congruent? Step number two, do the arcs have the same central angle measurement? Basically, are their slices the same size? Because if the degree measurement for the central angle is different, they're simply not congruent. It's a different number. If they're the same, then they're congruent. Okay, it's a pretty simple check, but we have to check both things. All right, so for part A. For part A, the red arcs are arc CD here on the left and EF here on the right. I'm checking to see if they are congruent to each other. So step number one, are the circles congruent? Well, there's only one circle here. So yeah, the circles are congruent to each other because it's the same circle. So that checks out. Number two, do they have the same central angle? Well, it actually explicitly says here that each central angle is 80 degrees. So yeah, they are congruent. Each arc is congruent to the other. Arc CD is congruent to arc EF. Part A, yes, they are congruent. Part B, just to break down the situation we're seeing here, this is an example that we saw in section 1. This is what we would call a situation of concentric circles, which just means that I have circles that share the same center. also called a bullseye or a target. Okay. And the red arcs we're comparing are the smaller arc here, arc RS versus arc TU. So for the record, again, my process is the same. I'm still checking two things. First, are the circles congruent? It should be very obvious here in this part B that no, they are not. One circle is quite obviously much smaller than the other. Okay, so already I know automatically the arcs are not going to be congruent to each other. The one interesting thing about this problem, the only reason it's kind of worth noting, is that the second question would be, do they have the same central angle? And actually, they do have the same central angle here. Because it's this kind of bullseye target looking thing, they actually share the same arc measurement, which is that both of these would have a 90-degree measurement to each of their arcs based on that little perpendicular box right there. But again, they cannot be congruent to each other because they're simply not congruent circles. So the answer here is that no, they are not congruent arcs. Two completely different circles. All right, part C. Sorry, it's a little small. I'll break it down for you. Here I have two separated circles. Right? So again, the checklist is the same. Are the circles congruent? Well, the only way circles can be congruent is if they have the same radius. And it's very difficult to see here. I apologize. But you'll see a little dash mark here for each of the radii. And that dash mark just visually means that, yes, they are the same measurement. It doesn't explicitly tell me how long it is, but that dash mark means that whatever it is, it's the same. So yes, these two circles are congruent, and it's purely based off its radius. All right, step number 2. Do they have the same central angle measurement? Well, again, difficult to see, but that's 95 degrees there. That's 95 degrees there. Yes, they are congruent. So arc UV is congruent to arc YZ. Done. All right, so again, punchline for those ones, are arcs congruent? Number 1, are the circles congruent? Number 2, do they have the same central angle measurement? Done with those. All right, last problem here is in the center of the notes. Find the measure of each arc. This is actually kind of similar to the first example we did, so I'll burn through this pretty quickly. It's just a different kind of set of information in the diagram. Here we're given a little more slices. Let me just break down what you're seeing because I know it's a little small. The small slice up here at the top, that's 40 degrees. This one here on the right is 80 degrees. And the one down at the bottom is 110 degrees. There is one slice that I don't know the information for, and that's this one here on the left. But again, for the record, I could still use that, what will now be considered an expected known fact, that all circles have 360 degrees on the inside of them. So you're all probably familiar with this. This is actually the arc addition postulate in action right here. I can add up these pieces to figure out what's left over for this one that's missing. Okay, 40 plus 80 is 120. That 120 plus 110 gives me 230 degrees. That's all the known degrees that I have, these 3 slices here. If I subtract that from the 360 degrees of what exists on a circle, that leaves 130 degrees for this missing slice here. So particularly for these kinds of problems where I have like multiple pieces to solve for, I would actually just start with filling in the unknown slices. So now I know every single slice here. 40, 80, 110, and we just solve for 130 over here on the left. Great. So now that I know these, now it will just ultimately break down to adding up the slices that make each of these respective arcs. So let's just go through the notation again. Part A, here's a minor arc, GE. So it's going to be the shortest distance between those two letters. There's G. E's down here. The shortest distance will be these 2 slices. What's the measurement of arc GE? Add up the pieces. That's arc addition postulate. 40 plus 80, 120 degrees. Measurement of arc GE is 120 degrees. Again, if you wanted to show work, it's the 40 plus the 80. Part B, major arc now. GEF. Just follow the letters G to E to F. So it's actually all the known slices. Again, it's just arc addition postulate. If you want to show work, it'd be 40 plus 80 plus 110. And we found that out already to be 230 degrees. Major arc GEF is 230 degrees. Part C, minor arc GF. This ends up being the one slice that I wasn't given the information. So G to F is this slice over here on the left. Again, if you want to show work, you could say like, all right, 40 plus 80 plus 110. If I subtracted that from the 360 total, that left me with the 130 degrees